Okay, we need to write the equation. The parent function is absolute value of x. It needs to be shifted down 10 units to the right 12. We'll start with the one that's to the right 12. Since it's moving left or right, it's affecting the x values. That means it needs to be inside of the function. It's going to be minus 12. Remember, since it's inside the function, it has the opposite effect of what you'd think. Moving to the right 12 is subtract 12 inside. And then shifting down 10 is minus 10 on the outside. Similar thing on 15, but there seem to be more mistakes when it's x being raised to the second power. It's being reflected about the x-axis and shifted to the right 7. So I'm going to start with that one. Shifting to the right. The function is a squaring function right here. So anything that occurs within the function needs to also be squared. And so keeping that in mind, it needs to be written this way, x minus 7. And the minus 7 is part of what's being squared, representative of inside the function. And then it's reflected about the x-axis. So there's a minus sign right there. And question 16, this is the equation right here that's the original equation, or the original graph, and this is x squared. So we've got to figure out what's happened here. First of all, it's moved to the right 2 units. It's moved up 1 unit. And it's upside down. So g of x minus sign because it's upside down, x minus 2 for shifting to the right unit, to the right 2 units, and then a plus 1. Okay, now algebraically, to determine if a function is even or odd or neither, you have to consider the function when all the x's are replaced with the opposite of x. So we evaluate the function at negative x. This turns out to be negative x to the 5th minus negative x to the 3rd, which is negative x to the 5th plus x to the 3rd. Now, once you've finished the evaluation, you've got to determine if is this the exact same function you started with, because if that's the case, that's an even function. If this is the exact opposite of the one you started with, it's an odd function. If it's some of it's the same, some of it's not exactly the opposite, then that'd be a combination of, that would be an example of neither. Now this one here, if we factored out a minus sign, we would have x to the 5th minus x to the 3rd. Now this right here is what we started with. This is f of x. And so this is the opposite of f of x. So f of negative x is equal to negative f of x, which is an indication of an odd function. Okay, question 17, or 18 rather, it's the same thing. We have to start off by evaluating the function at negative x. So this is 7, it's negative x squared, plus 4, but negative x to the second power is just x to the second power, so this is 7x squared plus 4, and that's exactly equal to h of x. So h of negative x is equal to h of x, which is an indication of an even function. Okay. 19, combine the functions using these operations and also state the domain. So f plus g these functions cannot be added unless they have a common denominator, so this expression on the left needs to have x minus 4, and this one on the right needs to have an x minus 2. So now both expressions have the same denominator, x minus 4 and x minus 2. In order for these two to be added together to form one expression, the denominators had to be defined. So before even adding these together, we probably should determine what the domain is. Domain x cannot be 2, x cannot be 4. And write that over here. The domain for part A, all values of x such that x does not equal 2, and x does not equal 4. Now this piece right here, numerator, that's 3x minus 12. This one right here is going to be x squared minus x minus 2. Now that they have the same denominator, they can be added together to form one expression. In the numerator, we're going to have x squared plus 2x minus 14, and then the denominator is going to be x minus 4 and x minus 2. Now f minus g, the only difference is going to be this right here will be a minus sign rather than a plus sign. So just going to copy this here. This is going to be 3x minus 12 over x minus 4, x minus 2, minus this time x squared minus x minus 2. So the result is going to have the same denominator, x minus 4, x minus 2. We have to be really careful. We're subtracting this entire numerator now. So it's going to be negative x squared. And then 3x minus a negative x is a 4x. And then negative 12 minus negative 2 is negative 10. And the domain for part B is the same as part A. X cannot be 4, x cannot be 2. Now, for part C, multiplying is going to be a little bit easier because you don't have to have a common denominator. So we're going to start with the original f function, 3 over x minus 2 times x plus 1 over x minus 4. These can be multiplied straight across. So 3 times the quantity x plus 1 is 3x plus 3, and then x minus 2 times x minus 4. The domain is also x cannot be 2, x cannot be 4. Now dividing 3 over x minus 2 times x plus 1 over x minus 4. Let's see, that should be divide. So in order for this division to even be possible, x can't be 2, x can't be 4, but you'll see at the end of this problem there's going to be an additional x value that's going to have to be excluded. So the domain for part D is going to be slightly different than for A, B, and C. Now rather than, well, the way that you divide fractions is to invert this second fraction, so I'm going to write it as a reciprocal x minus 4 over x plus 1, and now we can multiply. So in the numerator we're going to get 3x minus 12, and the denominator we're going to have x minus 2 and x plus 1. But let's talk about the domain. So we have the original excluded values, x such that x cannot be 2 and 4. But with the result here, x can also not be negative 1. So those are the 3 excluded values there. Now for question 20, this open circle means composition. So this is f of g of x. So the g function is going inside the f function. So we're going to take this function here and place it inside right over there. So this is going to be 4 over the square root of x plus 2. Now we have to rationalize the denominator. So it's going to be 4 times the square root of x plus 2 over x plus 2. So when we consider now this domain, There's two things we have to consider here. First of all, this is written in the form of a fraction, so we have an excluded value here. X can't be negative 2. But in the numerator, we also have a radical. So that also means that we can't take the square root of anything that's negative. So first focusing on the radical. In order to take the square root of x plus 2, x plus 2 has to be greater than or equal to 0, which means that x has to be greater than or equal to negative 2. But that's just for this piece in the numerator. We know now from the denominator that x cannot equal 2. So the domain is just strictly greater than 0. So this is strictly greater than negative 2. So the domain is the open interval negative 2 to infinity. I'm going to just explain this again. Although negative 2 is okay to plug in here for this x, it wouldn't be okay to plug in for that x down there, so negative 2 cannot be included. Now the part B here, g of f of x, means that the f function, so now I'm going to write this one another way, this f function here is going to go inside of the g function for that x right there. So the composition is going to be the square root of the input 4 over x plus 2. Now, if we combine this on the inside, write that as one expression, it's going to be, we can multiply that by x over x. This is 4 plus 2x over x. Now, this is going to have to be rationalized. We have the square root of 4 plus 2x over the square root of x, so we're going to need to multiply this by the square root of x over the square root of x. So what we're going to have there is the square root of 4x plus 2x squared all over x. Now, similar thing is happening here in the denominator that was happening here in part A. There's two things to consider. X can't be 0 because of this piece in the denominator, but 4x plus 2x squared has to be greater than or equal to, has to be greater than 0. It can't equal 0. So 4x plus 2x squared needs to be greater than or equal to 0. Otherwise, we couldn't take the square root of it. Now, the way that these are this is a quadratic inequality. The way this was done is to factor out 2x. That's going to leave a 2 plus x is greater than or equal to 0. This is kind of referring back to some topics in 1010, but once you have it in factored form, you find the zeros of this quadratic. So what would turn each of these factors into 0? Here would be x equals 0. Here is x equals negative 2. So negative 2 and 0. Then you choose test points in each interval. For example, let me do this in a different color here. Negative 1 could be a test point. 1 could be a test point, and negative 3 could be a test point. Now, if you plug in negative 3, 2 times negative 3 is negative 6. 2 plus negative 3 is negative 1. Negative 6 times negative 1 is 6. 6 is greater than or equal to 0. So this interval checks out because the test point worked. If you plug in a negative 1, then 2 times negative 1 is negative 2. 2 plus negative 1 is just a positive 1. Negative 2 times 1 is negative 2, which is not greater than or equal to 0, so this interval didn't work. And then positive 1, 2 times 1 is 2. 2 plus 1 is 3. 2 times 3 is 6. 6 is greater than or equal to 0, so that interval checks out as well. So we need all of these numbers on that interval. We need all of these numbers on this interval. And since it's greater than or equal to, we would normally include the endpoints. So we're going to include this endpoint of negative 2, but we're not going to include that endpoint of 0 because x cannot be 0. So the domain is from negative infinity to negative 3, union parenthesis 0 to infinity. Now we're finding the composition of two functions at a specific value of x now, not just at x. So this is find f of g of 2. So the 2 is going to go inside the g function first, forming a new number. We're going to take that new number and plug it into the f function. So let's first find out g of 2. That's going to equal 2 minus 1, which equals 1. So now g of 2 can be replaced with 1. So now we need to find f of 1, which is 6 times 1 squared minus 10 times 1 minus 8, which is 6 minus 10 minus 8, which is negative 12. Now this is g of f of 2. So the first thing we need to figure out is f of 2, because 2 is going to go inside the f function. That's going to change it into a new number. That new number goes inside the g function. So f of 2 becomes 6 times 2 squared minus 10 times 2 minus 8. 2 squared is 4 times 6 is 24 minus 20 minus 8. So 24 minus 20 is 4. 4 minus 8 is negative 4. So now we evaluate g at negative 4, which is negative 4 minus 1, which is negative 5. 22. Find two functions f and g such that the composition f of g of x would equal this. We did an example of this in the end of section 3.6 notes. So if we let little f of x equal the square root of x and g of x equal to x minus 2, then when we found the composition f of g of x, then this x minus 2 wouldn't go inside of this x right here, forming this function. So that's all really they were asking you to do on this problem, is find the two functions such that when you place them together, or when we form the composition, it would give you capital F of x. Now question 23, I mentioned this in class in lesson 3.7. There's only one acceptable way to answer 23. It's to show for part 1 that f of g of x is equal to x, and for part 2 you have to show the other composition f of g of x is also equal to x. So for part A, the g function is going to go inside the f function there, so this is 3 minus 4x all over 4. Now that turns into 3 minus 3 plus 4x all over 4. 3's cancel, so it's 4x over 4, which is x. So we've shown that the composition there is equal to x. Now the other way around, f of g of x, that means the f function here is going to go inside the g function right there. So this is 3 minus 4 times the f function, which is 3 minus x over 4. 4's cancel, so this is 3 minus x, which is 3 minus 3 plus x. 3's are gone, so we're just left with x, which shows that the composition going both ways is equal to x. Page 7. f of x is a quadratic function. And I mentioned this a couple times, but the domain of any quadratic function, whether it's facing up or down, the domain is negative infinity to positive infinity. Now the range, just by looking at the equation, might be a little bit tricky to find. If you consider a quick sketch of this graph, you go to the right one and up 3, and it's a parabola that's facing up. So on the y-axis, the smallest number in the range is 3, because there's no values of the graph that have a y value less than 3, so 3 is the smallest y value. The highest one is positive infinity, so the range is from 3 to infinity. Now, the function is not 1-to-1. And we can see here the graph, it's a parabola, it fails the horizontal line test. And because it is not, we need to restrict the domain in such a way that the function becomes 1-to-1. Now the function is not 1-to-1 because the parabola, it's going up to positive infinity on both sides. If we could get rid of one side of the parabola, either the left side or the right side, then that would do. So if we restricted the domain to 1 to infinity, for example, what we're doing is getting rid of that whole left side of the parabola, so all we would be left with is, starting with the next value of 1, we'd be left with the side, the right side essentially, which would then pass the horizontal line test. Now, we need to find and state the domain and range of the inverse. So first we need to find the inverse of the original function here. So that's done by switching the place of x and f of x. So it's going to be x equals the inverse of f of minus 1 squared plus 3. Now we need to solve for the inverse here. So we're going to subtract 3. We're going to square root both sides, so we have the square root of x minus 3 is equal to the inverse of f minus 1. We add 1 to both sides to end up with square root of x minus 3 plus 1 is equal to the inverse. Now, the domain and range of an inverse are the opposite of the domain and range of the original function. Now, we're not considering this domain anymore, we're considering this restricted domain. The restricted domain of the original function becomes the range of the inverse, and then the range of the original function becomes the domain of the inverse. Question 25. Graph an inverse. So to find an inverse algebraically or graphically, the phrase to remember is you switch the place of x and y. This point right here, for example, is the point 1, 0. If you switch x and y, then the inverse would be the point 0, 1. And also something to remember is that a graph and its inverse are reflections about that line. So the inverse would look about like that. Okay, 26 and 27, story problems here. There's going to be a question either like 26 or 27 on the exam. So these both, I think, are from the latter end of chapter 3, from 3.6, 3.7, that area. So for 26, a stone is dropped in a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. Now this quantity here, 60 centimeters per second, we need to be clear on what that's describing. That's how quickly the circle is expanding, and in particular that's describing how quickly the radius is expanding. This is not a quantity that's describing the area or the circumference. This is how quickly the radius or the diameter would be expanding. So a function g that models the radius as a function of time. So it depends on what variable, I guess, we allow time to equal, but most of the time is equal to t. So it's a function g that's modeling time, so it's going to be a function g of t. Now, when time equals 0, essentially the stone hasn't been dropped in the lake yet. When time is 1 second, what do we expect how far do we expect the circle to have expanded? And if it's expanding 60 centimeters per second, then after 1 second, it's expanded 60 centimeters. After 2 seconds, it's expanded another 60 centimeters, would be 120 centimeters. After 3 seconds, it would be 180 centimeters. So the function here that we could use is 60t. And let's see if that fits the data. When time is 0, 0 times 60 is 0. So when time is 1, 60 times 1 is 60. So after 1 second, it's expanded 60 centimeters, and so on and so forth. Now, a function f that models the area of the circle as a function of the radius. Now, the area of a circle is equal to pi r squared. Now we need to find a function f that models the area of the circle as a function of the radius. So again, it depends on what variables we're assigning here, but since we're talking about a radius, let's make this r. So f of r is just equal to this expression pi times the radius squared. Now f of g is what they're asking us to find. So f of g of t means that g of t is going to go inside of the f function for this input here. So it's going to be pi times the g function, which is 60t squared. Now the important question here is, what does this function represent? This function, first of all, if g is going inside of f is describing the area. But originally f was defined in terms of r. But what we have now is f being described in terms of t. So this is a function f that describes the area. But instead of describing the area in terms of its radius, this is going to be describing the area in terms of the independent variable now t. So this is a function that will give us the area at any given time t. So instead of having to know the radius to find the area, all we have to know is how much time has elapsed. Because depending on how many seconds have passed, you multiply that by 60 to find the radius, and that squared times pi will give you the area of the circle. Okay, 27. $50 off coupon, and then there's also a 20% discount. And X is representing the normal price of the cell phone. So let's say that you're only allowed to use one of them here, the 20% discount for part A. Find a function f that models the purchase price of the cell phone as a function of the regular price. So f, and it's going to be a function of the regular price x, so this is f of x. Now if 20% is being taken off, then we're only paying 80%, so we're paying 80% of the original price x. Now part B, suppose only the $50 coupon applies, find a function g. So this is a function g, and it's going to be a function of the sticker price x, so this is g of x. Now this is not a percentage taken off, this is just plain old $50, so we're going to start with the original purchase price and take off $50. Now if we want to use both of them, there's going to be a composition function. Now we can use the coupons in different orders, and what we're trying to figure out is, doesn't matter. is one more advantageous than the other. So f of g of x means we're going to apply, well, let me write it this way, f of g of x. So first the sticker price is going to be in the g function, means so first we're going to take the $50 off, and then we're going to get 80% off of that. So that's going to be 0.8 times x minus 50. Now the other way around is g of f of x, which is written this way. So we're going to take the original price, place it inside the f function, so that means we're going to take 80% off first and then subtract $50. So that's going to be 0.8 x minus 50. Now this one here needs to be simplified. This turns out to be 0.8x minus, then 80% of 50 is 40. So now we need to compare here. If x is the regular sticker price, the first thing that happens to x in both of these here is that we take 80% of it. Here it turns out that we're only subtracting 40, but here it turns out we're subtracting 50. So this one right here turns out to be the better deal. We should take the 80% off first and then subtract 50